When we want to discuss triangles, we can do so in terms of their angle measurements as well as their side lengths. That is, we can classify them in terms of these parts, where in the former cases, the way that we end up doing so actually has very similar language and follows very similar patterns to the things we saw when we were classifying angles, and that should be for understandable reasons based on the things we saw in terms of the measure of a straight angle and the sum of interior angles of a triangle. But in any case, if we want to discuss how we can say what a triangle is, we can do so first in terms of angles by saying that a triangle is acute if all of the angles within it are acute angles. That is, if all angles are less than 90 degrees. Meanwhile, if we have one right angle, then we say that the triangle is right. We call that a right triangle, where we get some very special relationships for right triangles that we'll see one of in a bit and a few more later. From there, we have what are called obtuse triangles, which result from having a single obtuse angle. From there, we can talk about classifying the triangles in terms of side lengths, where we call a triangle isosceles if we have two sides of the same length, or equivalently one length that is different from the others, where the angles opposite of the sides of same length also have the same measure. So you can also think of it as being a triangle with one unique angle measurement. Then we say a triangle is equilateral if all sides and angle lengths are the same, where the angle measurements will be 60 degrees each. And then we say a triangle is scalene if no two sides or angles have the same measurements. Where there are some special things that happen here in terms of those angle measurements happening to be the same that comes pretty directly from the relationship between triangles and rectangles and quadrilaterals, but all those are things to worry about in 10.3. For now, the other thing we can talk about here with triangles is the idea of similar triangles, that thanks to the, well, I guess you could say lack of options in terms of how a triangle can be presented, if we have that the sides and or angles of a triangle follow the same ratio as another triangle, we call these similar, where we say that the sides are corresponding sides if they have the same value up to the ratio, and the angles are corresponding angles where they will have to be the same because there's not a lot you can do in terms of ratioing out those angles when you've got so few to work with. But for an example, we have something like so up here in terms of what that looks like. So let's get one more for seeing how we can actually use this relationship in order to be able to find some measurements that might not be entirely obvious. For this example, we want to find the missing length x for the given triangles, where we have those side lengths as given and want the remaining. For this, what we want to notice here is the relationships we might have between our side lengths and angle lengths. And in particular, we can notice that the two almost opposite side lengths there are marked with the same angle measurement symbol. That means they're going to have the same measure there because they've got that cross with the notch in it. Then the parts in the middle, those are going to be vertical angles, thinking back to things we saw in the last section. So those two interior angles there have to have the same measurement. And then because we've got two that have the same measurement and the two in the middle that have the same measurements, the remaining pair also have to be the same because there's only so many ways you can remove things from 180 before you run out of options. So without any consideration for what those measurements actually are, because we don't actually care, they have to be the same. So, because these have to be the same, because we have the same angles in corresponding locations, we have the corresponding angles that we want, these are going to be similar triangles, which means that we will have consistent ratios between side lengths in the same relative location. So looking at the two that sort of jut across that vertical angle that are given, the 5 and the 8, we must have that ratio, 5 to 8, matches across to the angle 7, side length 7, with the missing side length x. That is, 5 over 8 is equal to 7 over x. And from there, we can actually just rearrange to get our value. That 5/8 equals 7 over x is the same as saying 56 equals 5x, cross multiplying, and then divide to get that x is going to be equal to 56 over 5, or 11.2. So This is the main use we have here for similar triangles, where we're looking for triangles that have the same angle set, which must mean they have side lengths that fit a consistent ratio. You can use this to find side lengths that are and are not given, or get ones that aren't given in terms of one that are, but a process we'll see some examples of in the homework and in the worksheet as well. For now, we're going to finish off our second section of the chapter here by looking at a very old and very famous result, specifically in the context of right triangles, the Pythagorean theorem.